We can use the principle of refraction to create optical devices that help us view things differently. A device that creates an image by refracting light is called a thin lens. A thin lens is usually circular, and its two faces are some portion of a sphere that can be concave, convex, or planar. There are two main types of lenses. A converging lens will bring the light rays to a focus, and there are three types of converging lenses. A double convex lens is just what it sounds like. Both sides of the lens curve out. A plano-convex lens is a convex on one side, but planar on the other, while a convex meniscus lens is convex on one side and slightly concave on the other. A diverging lens will spread light rays out, and it also comes in three types. A double concave curves inward on both sides. A plano-concave is concave on one side and flat on the other, and a concave meniscus is concave on one side and slightly convex on the other. The key difference between converging and diverging lenses is that the converging are thicker in the center, whereas diverging lenses are thinner. Just like we did with mirrors, we can use ray tracing to determine information about the image formed from different lenses. Consider the light rays coming to a double convex lens parallel to the principal axis. In this example, we are assuming the lens is made of glass or plastic with an index of refraction that is greater than the air outside. This means that according to Snell's law, the light ray will be bent towards the axis as it enters the front side of the lens, and again as it exits the back side. These refracted rays will intersect at a point called the focal point. The focal point is designated with a capital F and is found some distance from the center of the lens. Since the rays entering the lens are essentially parallel, we can say that the focal point is the image point for an object at infinity on the lens axis. This just means that the focal point of a lens can be found by locating the point where the rays form a sharp image. This distance, designated with a lowercase f, is called the focal length. Interestingly, if you turn the lens around so the light is traveling through the other side of the lens, the focal length will be the same, even if the curvatures of the two sides are different. In the case of a diverging lens, light coming in parallel to the principal axis is refracted in such a way that the rays exiting the lens are bent away from the principal axis. If we trace these rays backwards, we find that they appear to originate from a point in front of the lens. This is the focal point of the lens, and the distance to this point from the center of the lens is called the focal length. The strength of a lens has to do with the degree to which the light rays are refracted. This is specified in the power of the lens. The power is simply the inverse of the focal length, and as such has a label of an inverse meter, and we call this a diopter.